So now I'm going to try to reconcile what we learned about these distributions and the fundamental theorem or the fundamental result of kinetic molecular theory that said that energy depends on temperature alone. And if you've been thinking ahead about this, you might find an inconsistency. All right, so there is a formula that will tell you the actual root mean square speed. And it is this right here. So it's equal to the square root of 3RT over the molar mass. And it's, again, as we talked about before, usually a little bit beyond the highest point of the distribution. So it's a little bit faster than the most probable speed. The take-home lessons from looking at these graphs are that this root mean square speed increases with temperature, and that the distribution broadens as the temperature increases. This first point is pretty obvious from the equation, right? So temperature goes up, the root mean square speed goes up. And the distribution broadening is a much more complicated equation that we say for juniors and seniors, but you can see the result in the graphs here. All right, so again, we're also looking at this equation and now explaining the effect on these distributions as mass. So these are the speed distributions for a bunch of gases, all at the same temperature. And these are the molar masses written down here. And you can clearly see that, and again, this equation sort of, predicts this, that the molar mass here, it's in the denominator here in the equation, which means that as the molar mass goes up, the root mean square speed is going to go down. Or right, and that's exactly what I said here. So the fastest one is hydrogen, weighing in at 2 grams per mole. The slowest one of those listed here is O2, weighing in at 32 grams per mole. And the other thing that is not evident from this simple equation is that the distributions also broaden as the molecules get lighter. So just remember, the lighter ones go faster. Now let's talk about the potential inconsistency. So here's the equation we've been talking about and been showing you a lot, that the root mean square speed is equal to the square root of 3RT over the mass here, m. Now the fundamental result of kinetic molecular theory said that that the energy of a gas depended only on temperature, not its speed. But when you think kinetic energy, which is what you're talking about here, if an equation comes to mind, it's this one, 1/2 mv squared. And in this case, m represents the mass of the molecule, and v represents its root mean square speed, and we're just going to square it. Couple of things here. The two variables in this equation are not mentioned at all in kinetic molecular theory. It said that temperature only mattered, not mass or speed. And to make matters even more complicated, the one variable that kinetic molecular theory does say matters, temperature, is not in here at all. So was I wrong before or was I wrong later? So what's the deal here? And it's actually fairly simple to rectify. And basically all you need to do, so let's consider the energy of 1 mole of gas molecules. All right, so all I get here, so energy is m over 2, and then what did I do here? Well, all I did was I introduced or substituted this expression for the root mean square speed into this kinetic energy equation. So I've got, the 1/2 m over 2, and then instead of the v, I actually put in the square root of 3RT over the mass. And then if you square a square root, those two expressions cancel each other out, and you get m over 2 times 3RT over m, and the masses cancel, and you actually get an expression that depends on temperature only and not what the gas is. And in most chemical physics application, if something depends on the identity of a compound, or gas in this case, it shows up as a mass dependency. So the idea was that the kinetic energy depends on the mass and the root mean square speed, but the root mean square speed also depends on mass. those dependencies cancel each other out, leaving you only with that temperature in there. So the energy of a mole of gas molecules is just 3RT over 2. And so the mean energy of a single gas molecule would simply be the energy of the mole of them divided by Avogadro's number. And this is this little funky E that shows that we're talking about a single molecule and not a mole of them. So, kinetic molecular theory was right to begin with. Energy should in fact depend only on temperature and not what the gas is. So to restate, at a given temperature, the kinetic energy of all the molecules will be the same, but the speeds will not, and those of a lower mass, the lighter ones, will have a greater root mean square speed.